Announcing the arrival of Yang Berbahagia Professor Dr. Muhammad Iqbal Saripan, Deputy Vice Chancellor, Academic and International, University Putra Malaysia. Negaraku and Putra Gemilang. Please rise for the national anthem, Negaraku and Putra Gemilang. Please be seated. Assalamualaikum and greetings to Yang Berbahagia Professor Dr. Muhammad Iqbal Saripan, Deputy Vice Chancellor, Academic and International, University Putra Malaysia. Yang Berbahagia Professor Dr. Abdul Syukur Juraimi, Dean, Faculty of Agriculture, University Putra Malaysia. Yang Berbahagia Professor Dr. Cik Fauziah Ishak, Professor at the Department of Land Management, Faculty of Agriculture, University Putra Malaysia. Principal Officers, Tan Sri, Datuk-Datuk, Datin-Datin and honoured guests. Welcome to the inaugural lecture by Yang Berbahagia Professor Dr. Cik Fauziah Ishak. To seek blessing to today's event, I would like to call upon Ustaz Muhammad Nur Hisham Nordin from the Pusat Islam UPM for the doa recitation.
Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Ila hadratin Nabiyil Mustafa Rasulullah sallallahu alaihi wasallam Al-Fatihah. A'udzu billahi minasyaitonir rajim. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin, arrahmanir rahim, maliki yaumiddin. Iyyaka na'budu wa iyyaka nasta'in. Ihdinas siratal mustaqim. Siratal ladzina an'amta 'alaihim ghairil maghdubi 'alaihim waladdallin. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Wassalatu wassalamu ala ashrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Allahumma inna nas'aluka ilman nafi'a wa nas'aluka qalban khashi'a wa nas'aluka yaqinan sadiqa wa nas'aluka dinan qayyima wa nas'aluka amalan saliha wa nas'aluka khairan katsira. Allahumma inna nas'aluka minal khairi kullihi ajilihi wa ajilihi ma 'alimna minhu wa ma lam na'lam wa ma lam na'lam wa na'udzu bika minasy syarri kullihi ajilihi wa ajilihi ma 'alimna minhu wa ma lam na'lam. Allahumma ya Hannan ya Mannan ya Badi'as samawati wal ardh ya Dzal jalali wal ikram. Ya Allah, ya Tuhan kami, segala puji-pujian bagimu, ya Allah. Selawat dan salam ke atas junjungan besar Nabi Muhammad sallallahu alaihi wasallam, semulia-mulia Nabi dan Rasul, dan juga ke atas kaum kerabat dan para sahabat radhiyallahu an. Ya Allah, ya Tuhan kami, dengan segala sifat kebesaran dan keagungan-Mu, kami melafazkan kesyukuran atas rahmat dan kurnia-Mu yang mengumpulkan kami pada majlis ini. Semoga majlis ini dipermudahkan Engkau, ya Allah, dan semoga membuahkan nilai yang positif, memberi manfaat kepada semua, serta beroleh keredaan di sisi-Mu. Ya Allah, ya Tuhan kami, tetapkanlah iman kami, ikhlaskanlah niat dan usaha kami, teguhkanlah hati kami dengan kesabaran, luruskan tujuan kami dengan kejujuran, agar dapat kami hulurkan tenaga dan bakti dengan penuh ketulusan untuk membangun dan membina universiti ke arah pencapaian yang cemerlang. Allahumma ya Allah, ya Razzaq, ya Fattah, ya Alim, Engkau anugerahkanlah inayah, hidayah dan rahmat-Mu ke atas semua warga UPM dan mereka yang bertugas dengan penuh ihsan, dedikasi dan berkualiti. Ya Allah, ya Tuhan kami, hiasilah diri kami dengan ilmu yang bermanfaat, ilmu yang membawa kepada keluhuran akhlak kami, ilmu yang membawa kepada kami petunjuk dan pimpinan bagi membangunkan potensi dan kecemerlangan berterusan, tersusun dan terancang. Anugerahkanlah kami kekuatan ilmu dan kebijaksanaan untuk menerokai kejayaan. Jadikanlah diri kami insan yang berpandangan jauh, komited dengan kehendak dan perubahan zaman. Berikanlah kami kesihatan berterusan, ya Allah, agar kami dapat bergerak aktif menabur khidmat bakti kepada UPM yang kami sayangi ini. Ya Allah, ya Tuhan kami, jadikanlah perhimpunan kami ini sebagai satu perhimpunan yang dirahmati dan perpisahan kami pula selepas ini sebagai satu perpisahan yang diberkati dan dilindungi. Dan janganlah Engkau jadikan pada diri kami ini dan mereka yang bersama kami kebinasaan dan menyingkirkan kami dari memperolehi rahmat. Rabbana zalamna anfusana wa illam taghfir lana wa tarhamna lanakunanna minal khasirin. Rabbana atina fid dunya hasanah wa fil akhirati hasanatan wa qina adzaban nar. Wa sallallahu ala sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Walhamdulillahi rabbil alamin. Taqabbalallahu minkum minna wa minkum taqabbalakan. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Ustaz Muhammad Nur Hisham, for the doa recitation. Ladies and gentlemen, I would like to call upon Yang Berbahagia Professor Dr. Muhammad Iqbal Saripan, Deputy Vice Chancellor, Academic and International, to chair this inaugural lecture and to afterwards invite Professor Dr. Cik Fauziah Ishak to present her inaugural lecture. Please welcome Yang Berbahagia Professor Dr. Muhammad Iqbal.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. Salam sejahtera, salam satu Malaysia, salam We Love UPM. Yang bahagia Profesor Dr. Abdul Syukur Juraimi, Dean Faculty of Agriculture, Universiti Putra Malaysia. Yang bahagia Profesor Dr. Cik Fauziah Ishak, Professor at the Department of Land Management, Faculty of Agriculture, Universiti Putra Malaysia. Principal Officers of Universiti Putra Malaysia, Professors, Lecturers, invited guests, students, ladies and gentlemen. First of all, I would like to convey regards from Yang Bahagia Datin Paduka Vice Chancellor for not being able with us this morning. She got other commitments, but I'll be honored to be the person who going to introduce Yang Bahagia Professor Dr. Cik Fauziah Ishak in this occasion. Professor Cik Fauziah enrolled at the University of Iowa, United States, and graduated in 1981 with a bachelor degree in chemistry. And then she continued her Masters of Science also in chemistry right away in 1981 at the same university. She pursued her doctorate degree at the University of Georgia, Athens, Georgia, US, and obtained her PhD in agronomy in 1993. She started her career as a lecturer in 1985 at the Department of Soil Science, and now known as the Department of Land Management, Faculty of Agriculture, UPM. She's currently serving as a professor since 2015 at the Department of Land Management, and she is an expert in the area of chemistry of heavy metals in soil system. To date, she has served more than 30 years at UPM, fulfilling all the major responsibilities expected as a lecturer. She has been involved in teaching, very active in both undergraduates and postgraduate levels, and some of the courses that have been taught by her are like basic soil science and land resources and ecosystem, environmental soil science, soil and plant analysis, as well as land contamination and pollution. She was appointed in various administrative capacities, such as the head of department from 2007 to 2010, and she was also the deputy dean that in charge of academic, students affairs and alumni of Faculty of Agriculture from 2010 to 2016. As a professor and as a researcher, her subjects of interest are in the area of contaminated soil, with emphasis on heavy metals, contamination of soils, and assessment of land application of industrial byproducts, which is the mineral byproducts and biosolids, on crop growth performance, as well as soil fertility improvement, with special emphasis on heavy metals uptake by plants, which is becoming an important issue now in food safety and as part of the food security agenda in a whole. Her research also includes management of metal contaminated soils through in situ immobilization technique using industrial byproducts such as red gypsum, coal fly ash, and water treatment residuals. To date, she has handled and completed many research funded by the government, non-government funded projects, such as from International Atomic Energy Agency, IAEA, Australian Centre of International Agriculture Research, Indah Water Consortium, Huntsman Thai Oxide, and SKF Malaysia Sdn Bhd. She has been involved in soil, plant, and fertilizer analysis activities ever since she joined UPM in 1985. She is currently the coordinator of the analytical laboratory of the Department of Land Management at this faculty. As part of the involvement in the professional bodies and associations, she has been invited as the technical committee for various agencies such as RISDA, SIRIM, and Malaysian Institute of Chemistry on fertilizers. She has also been actively involved as a member of several professional societies, such as Malaysian Society of Soil Science, and currently serving as the Vice President since 2009. She's also the Chief Editor of Malaysian Journal of Soil Science, MJSS, from 2008, and in Management Committee of Agriculture Laboratory Association of Malaysia. She has joined that since 2013. She always strives for the best in whatever task been given to her, and she will always try to make the best out of that. She will continue to elevate herself towards greater achievement in the few years left as an academician in UPM. And as a conclusion, that it is no doubt that Professor Dr. Cik Fauziah Ishak has achieved excellence in all areas. We talk about teaching, research, as well as professional involvement in agriculture, particularly in solid waste management as written in the inaugural book. Let us now listen to Professor Dr. Cik Fauziah Ishak inaugural lecture entitled Solid Waste Management, Land Application of Agriculture and Industrial Byproducts. Thank you very much.
Okay. Yang berbahagia, Profesor Dr. M. Iqbal Saripan, Deputy Vice Chancellor Academic and International. Yang berbahagia, Profesor Dr. Abdul Syukur Juraimi, Dean Faculty of Agriculture, Universiti Putra Malaysia, Principal Officers of UPM, Professors, Lecturers, invited guests. In fact, I have a guest from Indah Water Consortium, which I have not met them for a long time, and lecturers, also my young and upcoming lecturers from local universities, from UITM, which are involved in the RACE grant, Dr. Azlan Kamari and Dr. Yong from UITM. Dr. Azlan is from UPSI. And also students. Actually today I have a group of land resource management students joining us for this inaugural lecture. Okay, thank you very much for making your time to come to this inaugural lecture. Okay, I would like to start my inaugural lecture. So the title of my inaugural lecture is Solid Waste Management, Land Application of Agriculture and Industrial Byproducts. So I would like to make a little bit of comment on the title itself. Yeah. So here I use the term industrial byproducts, because using the terminology waste, it has a negative perception. And people working in this area of research, we prefer, and I for one prefer to use byproducts because it has a positive outlook and it is telling you like this material has a potential to be used as a resource. Instead, waste means you want to throw it out. If resource, you will use it judiciously. Okay. So this is the outline of my presentation today. I will give you a very brief scenario of solid waste management in Malaysia, and then the establishment of soil, trace metal or metalloids investigation levels, followed by assessment of the suitability of byproducts to be land applied. Here I will use two examples as illustration, which I have been working on. And finally, I will touch on the area that is of special interest to me, which is in situ immobilization of trace metal or metalloids using byproducts, and finally conclude my presentation for the day. Okay, being a chemist, you cannot run away from showing the periodic table, because I want to introduce to you what is meant by the trace metal or metalloids. And in my presentation, I will interchangeably use the term trace metal metalloids, because it's kind of mouthful, and sometimes I will use the word heavy metals. This is a case where one terminology doesn't fit all. Yeah, that's why you see there is a conflict of using terminology to discuss all the trace elements that we are interested in. Okay, if you look at this solid line here, okay, the red solid line, anything on the right to the this solid line are non-metals. Everything on the left are metals. Yeah? But what are the trace metal or metalloids? This is in the purplish color. Yeah? But the problem is, yeah, some of the metal or metalloids are not traced in amount. For example, iron. Iron is a metal, heavy metal or metalloids, but is present in large amount. But the availability is not that much. Yeah? And metalloids are the elements, yeah, that is yellow in color, and arsenic is one good example of a metalloid. A metalloid is non-metal, but behave like metal. Yeah, that's why the term metalloids come in. Yeah? So, and then some metals that is of interest, like boron, for example, is not heavy. Heavy metals means their atomic density is greater than 6 grams per centimeter cube. So that's why I said one terminology doesn't fit all. Yeah? So some people use trace element, some use trace metal or metalloid, some use heavy metals. And I will choose to use heavy metals and trace metal and metalloids interchangeably. This is truly the heavy metal, yeah? Not the heavy metal rock band. Yeah? Okay. Okay. So I want to show you the solid waste management hierarchy. I think all solid waste managers, yeah, they are aware of this hierarchy, and if possible, when you are managing the waste, you want to, first of all, try to reduce the waste, and then try to reuse, try to recycle, and try to do intermediate processing if possible, and finally dispose it. Yeah? But what is happening currently? In 2014 report, in the Mega Science Framework of National Development, there is a workshop organized by National Academy of Sciences. That mega framework is from 2013 to 2050. Okay, in this mega science framework, it was reported that only 5% of the solid waste are recovered, and 95% goes to the landfill. So that is the current status. And in 2015, the United Nations has launched a program called Sustainable Development Goal. And Malaysia is committed to the Sustainable Development Goal. It's called Agenda 2030. Because by 2030, we have to achieve 17 goals in the Sustainable Development. And in the recent report on Sustainable Development Goal, a voluntary review, 2017, by Malaysia, we sent a report to United Nations. It was reported that in 2016, the solid waste that is recycled is only 17%. And the intended target by 2020 is 22%. But what I'm trying to tell you is that most of these solid waste that has been focused on, even in the mega science framework and in the sustainable development, the focus is on municipal solid waste. Very little report is on other solid waste. Yeah? So if you want to browse on solid waste management using Dr. Google, the thing that will come out most often is municipal solid waste. Not much on other report, and very difficult to get hold of the information. And most of the waste that I'm going to discuss, the solid waste, is classified as scheduled waste, mainly because of the heavy metal content in the waste. Because my expertise is in heavy metal content, so I'm not going to discuss about the organic contaminant that might be present in this waste. So when you are embarking on solid waste management, and if heavy metal is the element of interest, the first thing that you want to ask is, if you collect a sample from a site, is that heavy metal naturally or native or indigenous in the soil, or is it contributed by anthropogenic activities? That's why people doing research in heavy metal, the first thing that they need to do is to establish the heavy metal baseline or background value. Because unlike organic contaminants, most of the time, heavy metals, they can be present naturally due to the parent rock or minerals in the soil. So that's why the first task that I did when I started the work on heavy metals was to establish soil trace metal or metalloids. In this case, it's called investigation level. I will tell you why we call it investigation level. And the first project that I managed to secure some grant is the Australian Centre of International Agricultural Research project. It started in 1998. It's a 2-year project. We didn't receive much money from Asia. And in this project, there's 3 parties involved. The coordinating body is Cyro Adelaide. The person in charge is Professor McLaughlin from Cyro Adelaide. He is also attached to the University of Adelaide. And the other 2 parties are Malaysia, which I am the principal investigator, and Department of Agriculture Thailand. Dr. Pichit, I think, was the person. I can't remember his last name. 20 years ago, so it's quite a long time ago. And I have a good team working with me to do this project. So the title of the project, Assessment of Pollution of Agricultural Land and Crop by Heavy Metals and Other Contaminants. So the objective of the project is actually to check on the status of heavy metal contamination on agricultural soils and also in the crops, the uptake of heavy metals in crops, but the focus is only on Peninsular Malaysia. And we don't have time to collect samples from East Malaysia. And for this project, this project is sort of like a reconnaissance survey. That means it's not a detailed survey. And what we did was we go around Peninsular Malaysia and we covered the intensive vegetable growing areas such as like Tangkak in Johor, Cameron Highland, and some other mainly annuals, but mainly vegetables and annual crops, and also we include oil palm. And when we did the sampling, we were assisted by actually most of the farmers' plot that we sampled were under the Department of Agriculture Advisory. So it was easy for us to gain access to the farmers' land to collect the sample, and we do pet sampling. We collect soil sample and we collect the plant that is growing, the crops that's growing on that land. And what we did was then, we sort out the data. The number of samples was 241. We sort out the data and list from the lowest value up to the highest value. And the values at the 95% is taken as the 95% investigation level. Yeah? So if you look at the numbers there, like for example, cadmium, 0.30 milligram per kilogram, that is considered quite low. And it seems that when a colleague of mine was looking at the data, they say that our agricultural crops is not really contaminated. It's quite very low in contamination. So we did that for the 9 heavy metals, and this will be used as a benchmark to compare. If we do sampling and we see that there are elevated levels of heavy metal, so we have to start doing the investigation. I mentioned to you the soil baseline or background value is quite impossible for us to do that sample collection, because for baseline value you have to collect from uncultivated or forested area, which forested area is not easy to gain access because of the thick undergrowth. So the land use that is least contaminated in heavy metal is actually agriculture. Next is residential, and the most contaminated with heavy metals is the industrial areas. So what is recommended for countries that do not have soil baseline or background values is to establish the 95th percentile investigation level. And then if you look at, we subjected the data to principal component analysis. And if you look at the, so look at the cluster at the bottom. So if you look at the heavy metals, here you have iron, cobalt, lead, zinc, nickel, and is strongly correlated to the aluminium and iron. So that means the variation in the background is due to changes in the mineralogy of the soil. So this is what we call the geogenic sources of heavy metal. They are coming from the parent material or the rocks. And if you look at the top cluster in red, you can see arsenic, copper, cadmium, boron, selenium. They are highly related to total P, available P, organic carbon. That means they are associated to agricultural input, which is the fertilizers that you're using, the P fertilizers that you're using, and organic matter is mainly coming from chicken dung. So organic farming is using chicken dung, and chicken dung also contain heavy metal. And mercury stands alone. So for mercury, is they call it diffuse pollution from aerial deposition. It's not correlated to any other soil fertility parameters. So next, we move on to assessment of the suitability of byproducts to be land applied. In this case, I'm going to focus on two, in fact, domestic sewage sludge. Most researchers, they lump it also under industrial byproducts, because with rapid urbanization and industrialization, you will see that some of the domestic sewage sludge is also mixed with industrial sludge. And the next one, we'll look at paper mill sludge. Okay, this one I took from IWK report in 1990. If Mr. Sasi, if you remember, you presented this at the FAO IAEA coordinated meeting, which was hosted in Malaysia, so on sewage management in Malaysia. And what I want to tell you is that municipal wastewater sludge or sewage sludge has been and will always be a major management issue in Malaysia. As long as there are people living on there's Malaysian around, that sewage sludge will always be an issue. And it is also of global interests. And according to Mr. Sasi, actually before 1994, sorry, prior to 1994, before IWK, Sendirian Berhad took over the national sewage management, most of our rivers are polluted with domestic sludge. So I think IWK is given the task till 2022. That's why you see the prediction is up to 2022. Probably they will get a renewal. The contract will be renewed probably because they have done a good job. But you can see that in 1994, the annual production of sewage sludge is 3 million metric cube, and in 2020 is estimated to be like 7 million cubic meters. I hope that is what is happening, because some report says it's going to 10 million cubic meters. And if you're not, if you cannot imagine how much waste that is, according to Mr. Sasi, it's like, you know, you're filling the KL Twin Tower 2 times. That is the amount of sludge that you have to deal with. That's a lot of sludge. Okay. Okay, and when you work with sewage sludge, okay, this is an aerial view. One of the system there, you can see on the right, that is the extended. This one, extended aeration lagoon. This is probably sewage sludge lagoon. So what we did was, when you work with any byproducts, you need to characterize. If possible, complete characterization. But since I'm focusing only on heavy metals, so I'm just going to focus on heavy metals in the sludge. In fact, we also look at the organic contaminants. But what I want to bring to your attention, this sludge was provided to us by IWK. They are very supportive. In fact, for the FAO-IAEA project, I approached them and they support by giving the materials for us to work with. If you look at, I want to bring attention to you, the sewage sludge sampling sites at number 9 and 10. You can see that there are domestic sludge that is mixed with industrial sludge. Taman Perindustrian Puchong Industrial Park. So if you look at the sludge, most of the time when we want to land apply sludge, the thing that the element that we are focusing is on nitrogen. Sludge as nitrogen fertilizer. And the next question, whether is it safe to be land applied? Okay. So if you look at percent nitrogen, you can see at different sites, you know, the nitrogen is variable. And as the sludge, actually, it depends on the diet and the lifestyle of the household that is releasing the sludge. So that means as Malaysia become more developed, maybe our nutrition, maybe the younger generation, they consume more protein, maybe the nitrogen will increase. This was 20 years ago. And if you look at sludge number 9 and 10, the 2 heavy metals that is of concern in sewage sludge is copper and zinc. And if you look at sludge number 9, the zinc cannot be land applied. I mean, the sewage sludge cannot be land applied because the zinc is above the European Union maximum permissible concentration. So 2 of the sludges there and number 10. So it seems that it is not a good idea to mix industrial sludge with municipal sludge, because then it will be more difficult to dispose of this sludge. Even our expert from UK, they were telling us that UK has a centralized wastewater treatment system where they mix domestic and industrial, and they are trying to go to separation, yeah, between the two kind of sludge. Okay, for the FAO IAEA project, yeah, this was conducted in 1996 till 2001, and in fact, for this project, we have we have to grow 5 corn cycles. Yeah? So this is what I'm telling my student, yeah? Because in agriculture, there is what is called reproducibility crisis. If you do one cycle, it might not tell you the whole story. So 5 cycles, and then you can see what is happening during the 5 cycles. Yeah? And here, we are using N15 isotope study to trace the amount of nitrogen that is derived from the sludge. Yeah? It's an isotopic technique. And for this study also, treatment number 1, we are using the synthetic or chemical fertilizer as a comparison. And we have a control, T2 is a control. And if you look at T3, treatment 3 until 6, you see there are actually the sludge we were required, those who participate in this program, we need to sanitize the sludge by sending it for gamma irradiation. So I have one team member from Malaysian Nuclear Agency to do the gamma irradiation, so it's free of charge. Yeah? And the reason is to sanitize the sludge, mainly for the safety of the workers handling the sludge, and we want to compare with non-irradiated sludge. And also there is a theory that says that when you irradiate the sludge, there will be slight nitrogen loss from the sewage sludge. So for field preparation, yeah, so we prepared the subplot of 15 plants. Yeah, this is where we will apply the N15 labeled fertilizer. At that time, when we start the work, there's no nitrogen 15 labeled sewage sludge available. So we had to do indirect technique. So we use N15 labeled ammonium sulfate, 10% atom excess, yeah, to apply in solution form. So we have the subplot for 15 plants is growing, so we try to apply the sludge as homogeneously as possible, yeah? And then our yield plot, yeah, is 6 meters by 3 meters. So the samples that we collected are from the 15 plants in the subplot. So if you look at the mean total dry weight, yeah, from the experiment, so what is more important? The trend shows that the dry weight is higher, yeah, for the sewage sludge treated plot compared to the control, and is comparable to the chemical fertilizer, but it is not significantly different because of high spatial variability. The first corn cycle, the spatial variability is quite high, so you don't see the difference statistically. And if you look at the economic crop yield, when we say economic crop yield, this is sweet corn. Yeah? It's corn that is more than 100 grams, and you can still sell it as corn on the cob. And so that is what we call economic crop yield, and you can see that using the sludge give comparable yield to the synthetic versus the control. The control, the nitrogen in the soil is still a lot there that can be used up by the plant. So here, if you look at the red bar, this is nitrogen derived from sewage sludge. We have to do a little bit of calculation, and then the blue bar is the total nitrogen uptake. So when we look at the whole uptake, it seems that about 40 to 75% of the nitrogen is derived from the sludge. Okay. So it can vary because the external factor change. And the other thing is that I'm going to tell you that I'm not going to recommend those who are interested to use the sludge to use sludge as a sole nitrogen fertilizer, because nitrogen mineralization from the sludge requires optimum moisture condition. If the moisture is not there, the nitrogen will not come out and it will affect the yield. So it's good to combine synthetic and sweet sludge, so that synthetic chemicals will act as a fast release nitrogen fertilizer, and your sweet sludge as a slow release nitrogen fertilizer. Okay, so if you look at the concentration of copper and zinc in the corn grain, so you can see that what is important here, we compare it with the Malaysian Food Act and Food Regulation, the Food Act 1983 and Food Regulations 1985, and for both zinc and copper, they are below the maximum permitted concentration. So this sludge is safe for consumption. But I'm not also encouraging for people to apply sludge. You have to be very selective of the crop that you grow. It's not recommended for leafy vegetables, which is in direct contact with the sludge. If you grow corn, it's not in contact with the sludge, and you have the sheath of the cob that will protect the grain. So that will ensure that the corn is safe for consumption. So in 1999 to 2001, IWK has some money to provide grant. Actually, RMC approach, actually headed by Prof Azni. We approached IWK and they gave us quite a huge amount of money. So there were 5 projects that were placed under that grant. And I am the principal investigator for project number 1 on utilization of sludge as a fertilizer. It's multidisciplinary. It involves like faculty of engineering. They're looking at dewatering of the sludge using moronge plant. Dr. Falko Razi. Prof Muhammad Ali Hassan was looking at composting of the sludge with municipal solid waste. Dr. Azani from forestry was looking at sludge application to rubber plantation, and we have 2 in Faculty of Agriculture. The other one is slope stabilization using sludge by Dr. Mokhtaruddin, who has retired from Department of Land Management. So I headed this project, and we conduct a trial at the Share Farm, and here we apply sludge at, we use also the chemical fertilizer, the control, and then at the equivalent rate of the nitrogen that is present in the sludge 2 times, 3 times, and 4 times. And for this project, 3 cycles of corn were grown. Okay, so if you look at the first cycle, so if the important thing is that the sludge treated plot gave comparable total dry matter yield to the chemical fertilizer, just like the FAO IAEA project. If you plot this is sort of like a dry matter or a yield calibration curve, you can see that the optimum dry matter yield is at 420 kilogram N per hectare, which is about 3 times that of the synthetic fertilizer. This tells you that only 30% of the nitrogen is mineralized during the 70 days of sweet corn growth. So that's why I'm saying it's acting like a slow release fertilizer. So if you look at the visual yield here, the crop yield, T1 is the synthetic fertilizer, T3 is the equivalent nitrogen rate, and then for the bottom picture here, this is synthetic fertilizer, this is 2 times of the nitrogen equivalent rate. So the next study that we did for IWK was to look at sludge as N fertilizer for ornamentals. So in this case, we use 6 treatments, no sludge, and then chemical fertilizer, which is urea, and then incremental of nitrogen in rate in the sludge up to 100% of sludge. And so T1 is the control, T2 is the chemical fertilizer. So if you look at the plant performance, so what we did was we make sure the plant is adapted to the soil condition, and then we cut it 10 centimeters from the soil surface, let it grow, and during that time we apply the sludge. This is the practice that we do, and we split it into 5 splits. That means we are applying sludge every month. But the total is equivalent to the what is required for the plant growth for a year. Then we do the cutting. So it seems that from that treatment, we see that the sludge treated plot gave more vigorous plant growth than the chemical fertilizer or the untreated plot. And if you look at the total number of flowers, you can see that the chemical, this is the chemical fertilizer, equivalent rate will be T6. You see the number of flowers is significantly higher than not using the sludge. Okay, and the quality of the flowers is not affected by the heavy metal present in the sludge. So the next experiment, we want to substitute the standard practice, treatment 1. This is a potting media, 3 parts of soil, 2 parts of peat, and 1 part of sand. The standard potting media. And what we want to do in this case is to substitute the peat here with sweet sludge, because using peat actually is not an acceptable practice or green practice. We call it good practice because you are exhausting or depleting the natural resource, which is peat. And using peat sweet sludge alone will result in poor drainage, which will affect plant growth. So that's why we add coconut coir for better aeration. Actually, we have horticulturalists to help us. Dr. Tuhira, I'm not sure whether she's here or not, but she was the one that advised us on the cultural practice. And if you look at treatment 3 up to T5, this is a 2 sludge to 1 coconut coir, and then from T6 to T9, sorry, 3 parts of sludge to 1 part of coconut coir. Generally, these 3 parts of sweet sludge to 1 part of coconut coir give better growth than the 2:1, with the exception of T5. And Agro Blend is a slow release fertilizer, and foliar we use Agroforce. After 8 weeks of growth, you apply Agroforce at week 8 and every 2 weeks. So this is how the plants look like for at the early growth. This is the standard practice, and T8, T9 is the 3:1. So at the early stage, you don't see the difference very much. But at the full bloom stage, that is 3 months after it has been grown, you can see the number of flowers, the standard practice. You see T1, the standard practice, and T8 and T9, 3:1 mixture, it gives comparable number of flowers. And the flowers are not affected by the heavy metals. So that means sweet sludge can be used as a peat substitute for growing ornamentals. So if you look at the visual observation, you can see T8 and T9, the 3:1, and T8, you have agroblend. T9, you have half agroblend and half foliar. So it gives comparable result with the standard practice. Only the flowers are slightly smaller, but to me it looks cuter. And then I think if I am the person buying the ornamentals plant, I don't mind getting the smaller flowers, but many flowers. So it is good to know, right now, Malaysia have her own, they call it the Proposed Sewage Service Department Interim Guideline for Biosolids as Fertilizer. This is proposed by IWK. So we have a guideline value that is in red, and is for non-food crop. In fact, MyGap, Malaysian Good Agricultural Practice Certification, and My Organic certification prohibits the use of sewage sludge. So it can only be used for non-food crop. So I would like to share with my colleagues from IWK. This is an article taken from Chemical and Engineering Newsletter, November 2017. I extract the table out. It says, wasted opportunity, a broad portfolio of process for making chemical products from sewage sludge. So this is what is happening, or in the pipeline. It's going to happen in the developed countries, and I'm highlighting the fertilizer application. So they have phosphorus fertilizer, but this is a refined process, and then you have energy and fertilizer, and you have also this is more of a local production. So you can see that sludge can be used to omega-3 fatty acid food additive, with whether the public can accept or not. That's why in my title of presentation, I did not use the word sustainable, because there's still perception the public might not want to accept this product if they know where it's coming from. So next, I will move on to paper mill sludge. Actually, the work on paper mill sludge is also a biosolid. The work on paper mill sludge is of interest to my colleagues from FRIM. At that time, my student was also attached to FRIM. And for paper mill sludge, there is no consortium to look after the interests of the paper mill managers or operators. Unlike in more developed countries like Canada, they have paper and pulp or association to look after their welfare. So in this case, the sludge is subjected to Department of Environment's regulation. And the thing that we are not so sure is that some of the sludge are classified as scheduled waste. Some they get away from being scheduled, from being subjected as scheduled waste. So if you look at the chemical characteristics of raw paper mill sludge, You see that the recycled paper sludge, it seems that it is in compliance with the EU regulation. And we also look at the polyaromatic hydrocarbon and dioxin, and is below the level. And this paper sludge is wet, sticky, and it can cakes and emits strong aeration. So that's why composting with oil palm empty fruit bunches is recommended. And you can have a look at it at the poster board behind. This is the work of my student, Dr. Rose Azlin, which is attached to So for this project, we have glasshouse trial and field trials, and we have a control in the field. This is done at the Puchong Experimental Station, and then you use inorganic fertilizer and the composted sludge and the raw sludge. And after 1 year, the raw paper mill sludge gave the highest plant growth. And this plant is grown in the agroforestry system. You have the kaya trees in between. We intercrop with misai kucing or Otosipon staminus, the scientific name. And to look at the environmental impact, we install slim tube porous cup sampler in the soil to monitor groundwater up to 125 centimeter. And we collect the water and analyze for the heavy metals. So when we look at the concentration of heavy metals in soil after 1 year, most of them are below the 95% investigation level, with the exception of cadmium, which I mentioned to you was quite low. And then, but if you compare it with the ecological investigation level, the Australian regulation, it is below that level. So next I will move. This is actually the focus of my all my research interest that is current. So I'm just going to touch briefly on the main chemical processes which control trace metal or metalloids mobility in the soil, which is precipitation and adsorption. And precipitation is related to the pH of the soil system, and adsorption is related to pH also. You will control the charges, and the charges is on the soil component, which is the clay and the soil organic matter. So not to scare you so much, but I will show you afterwards the microscopic view. So actually our Malaysian soil is generally acidic, so liming is a common practice. So by doing that, unintentionally you're controlling the mobility of heavy metals. But now what I'm suggesting is that you can use the byproduct, because some byproducts have, they are alkaline, they have acid neutralizing capacity, and you can substitute it for lime, and it can also act as adsorbent to the heavy metals in the soil. So this is to show you one component of that will adsorb heavy metals in the soil. This is a 1:1 clay. So this is what we call the H group in the layered clay. And this is where you have the pH dependent charges. So if you change the pH of the soil, you can increase the charge. And adsorption is a surface phenomenon. So your heavy metals will stick to the surface of the clay materials. And for heavy metals, it's a specific adsorption. There's a ligand exchange mechanism. It's a stronger adsorption than the normal adsorption. So another simplistic microscopic view of I'm using biochar as an example of soil organic matter. Biochar is of recent interest, and we have biochar Association of Malaysia, BMA, many young scientists are looking at the biochar. So there are three mechanisms there. So you can have calcium, heavy metal exchanging with calcium and magnesium, and then the magnesium release can co-precipitate with the heavy metals, or you can have surface complexation with organic functional group, and finally you can have also physical adsorption or surface precipitation at the surface of the biochar. Yeah? Biochar actually is considered as a robust soil amendment, in fact, and also is termed as a green environmental sorbent. Yeah? So it's something to be exploited. And I'm in fact suggesting to IWK, it's a biosolid, you can convert it to biochar, yeah? And it can be used for land application. Yeah? So macroscopic view in general, yeah? The higher the pH, the more metals will precipitate out, or in fact it can be absorbed to the clay or the organic matter in the soil. Yeah? So that is the thing that we are going to look at in the byproducts to be used for in situ immobilization of heavy metals. Yeah? So I'm going to touch on biochar because it's of current interest. Yeah? And red gypsum, which I've worked for quite a long time since I came back from from my PhD study, and something interesting, yeah? Drinking water treatment residue. Yeah? This is a mineral byproduct. Yeah? So you can have biochar from different feedstock. Yeah? And right now we don't have sewage sludge derived biochar, no paper mill derived biochar for me to do work on, but you have publication from overseas where people are looking at it. And in fact, if you convert sewage sludge to biochar, you can reduce the sludge volume. You can completely eliminate pathogens and parasites. I forgot to mention to you what is of concern in sewage sludge is the parasite Ascaris, non-segmented worm. So we don't want the Ascaris to infect the workers. And then also by pyrolyzing the sludge, you are fusing the heavy metals into the biochar matrix, and it becomes less available. So that remains to be tested. So this is an opportunity for the young scientists who are interested to pursue biochar, to use biochar in the project. You can approach probably IWK, get the biochar and do the testing. So there's the biochar that we are using is empty fruit bunch biochar because you have a huge amount. The one that we use was from Nasmeg, Sdn Bhd. Actually, that they have the pilot plant, they produce the biochar, but now it's no longer in production. For sludge, for you to encourage farmers to use the sludge, the cost of the biochar, the cost of the biochar should not be more than RM1 per kilo. If for the Nasmeg, they are charging like RM2 per kilo. So there are no takers. So now they are thinking of changing the pilot plant to produce biofuel. And rice husk, no problem. There is commercially available rice husk biochar, and it costs about 60 to 80 cents per kilo. So this is the morphology of the biochar. The surface morphology is important for the absorption purposes. So if you look at EFB biochar, this is the side view, the front picture here. So the pores are uniform, smooth, And if you look at the top, you see the small specks there are the ash. So it seems that this EFB biochar is a good quality biochar. Good quality biochar, less ash. Yeah? But for the rice husk biochar, the pores is not well structured, diminishing pores, and a lot of ash. Yeah? Moderate, or perhaps you can class it as low quality. And if you look at the pore diameter, so the smaller the pore size, the higher the surface area, the higher the absorption capacity. That's what I'm trying to say. And with the ash, if you look at rice husk ash, the pH is much higher because of the ash content. Yeah? So EFB have higher surface area than rice husk biochar. And if you do Fourier transform infrared, these are the functional group. Yeah? So you have more types of functional group to have surface complexation with the heavy metals. The top one is the EFB biochar. The bottom is for your rice husk biochar. So if you do absorption study, you see that more this Qmax at the bottom here, this is the maximum arsenic. We are interested to look at arsenic in situ immobilization. So EFB biochar can absorb more arsenic than the rice husk biochar. But in this case, we are using arsenic 5 salt to do the absorption study. I'm just going to share with you a work done by Dr. Samsuri in my department. So he is using arsenic 3 and arsenic 5, and it seems that arsenic 3 is more highly absorbed than arsenic 5. And if you coat, in fact, if you read at the bottom here, coating the biochars with iron 3 greatly increase the absorption capacity for both arsenic 3 and arsenic 5. Actually, heavy metal research currently is not enough to determine total arsenic, but to determine the arsenic speciation. Arsenic 3 is toxic, arsenic 5 is not toxic. Yeah? So I'm going. So if you look at incubation study, you see with rice husk with biochar treatment, you have less water-soluble arsenic, and you also have less extractable arsenic. Yeah? So we have the glasshouse study looking at the increasing rate of EFB biochar and also increasing rate of rice husk biochar. And if we analyze the data, actually the rice husk biochar, the biomass, the aerial biomass significantly increased compared to the control. That means the ash release nutrient, and that increase the aerial biomass. Unlike EFB, which is a good quality biochar, but is not releasing nutrient to the plant. Yeah? So for the glasshouse study, using biochar at the rates of, in fact, at the rates of 5 ton carbon per hectare is good enough to remove extractable arsenic and also decrease arsenic uptake. Yeah? So I'm going to go very fast into red gypsum. This is a mineral byproduct from the titanium dioxide industry. And what happened is that they are extracting titanium, and the excess acid, spent acid, is passed through calcium carbonate bed, and that the acid is neutralized. So what will happen is that in this red gypsum, you have residual calcium carbonate present in the red gypsum. And if you look at the mineralogy, red gypsum is rich, we call it iron-rich byproduct, and the iron-rich byproduct can contribute to surface positive and negative charge because it is also pH-dependent charge. Yeah? So the red gypsum is as good as analytical grade gypsum in terms of solubility, and in fact, if we need to use calcium above what is given in liming, you can use red gypsum. And if we, in this study, we want to combine sludge-treated soil which have high iron and copper with red gypsum to see whether the alkalinity in red gypsum can reduce the heavy copper and zinc, as well as also precipitate out the copper and zinc. So if you look at the incubation study, 2.5% of red gypsum is enough to remove water-soluble zinc. And in terms of plant uptake, you can see that about 10% will reduce the uptake by the corn. So the last one, finally, I hope you bear with me, because this is special, because this drinking water treatment residue is actually a request by the drinking water treatment plant manager. And he is asking for help for somebody to look into WTR, whether it can be disposed on land, because his sludge lagoon is filling up, and he is thinking ahead of time of what need to be done. So this sludge was collected at Loji Pembersihan Air water treatment plant Sungai Selangor, and at that time is the highest drinking water treatment plant, the largest in Southeast Asia. Now I'm not sure, and they use alum for treatment. Alum is aluminium sulfate. So the concern here is that if you use this alum, whether it can cause aluminium toxicity to the plant or also to the animals eating grasses grown on aluminium contaminated WTR land. So that is being investigated. So actually the suspended solid in that in our river is about 50 to 100. So for just this one drinking water treatment plant, the annual production of the sludge is about 50, annual daily production is 50 to 100 tons. So imagine, I did not keep track of how many drinking water treatment plant we have in the country and what are they doing with the water treatment residue that is collected after treating the water. So if you look at the mineralogy, so what is present in the sludge is the clay minerals, kaolinite, elite, kaolinite 1:1 clay, elite is 2:1 clay, and gibbsite. So aluminium is now transformed to gibbsite. So it looks like the aluminium is not really available for plant uptake. So when we did the plant analysis, the aluminium concentration is comparable to the control. So if you look at the treatment here, probably 10% of WTR is enough to bring zinc out of the soil solution. And also in terms of uptake, you can see that about 5% can do the work. For copper, maybe you need about, if you want to bring out more, maybe 10%. So the last part, conclusion. Okay. So there is great potential of agricultural and industrial byproducts utilization in agricultural soils. But the thing is that the recommendation, not advisable to use byproducts as sole plant nutrient. Co-utilization is recommended, and large-scale field trials are essential. So overall, land application of agricultural and industrial byproducts is a holistic approach. You have to look at it as a whole. We should not be pursued only with the sole objective of converting waste into agricultural resources, but also importance is the preservation of the environment and ultimately human health. So I want to share with you, in Netherlands, the sewage sludge is not free for all to use, but only selected companies are given permits to land apply the sludge. And I think IWK is doing that, because I know one company came to see us and they have some agreement with IWK to utilize the sludge. And in US, for example, WTR and byproduct gypsum, there is guideline for land application. And I hope we will go towards that direction in the future. With that, thank you for your attention.
Thank you, Professor Dr. Cik Fauziah, for the outstanding presentation. Well, I guess now all of us know how professed she is in the area of solid waste. Yeah, and I think she started her presentation just now by saying that in her presentation, she will interchangeably use the word of trace metalloid. Yeah, trace metal, metalloid with heavy metal. Yeah, but we know also from the presentation that heavy metal cannot be interchangeable with metallica or iron maiden and etc. So the context of the lecture is very useful to all of us. Well, this is not my area, but at least I know how important it is for us to manage the solid waste. In a quest for the better management of the solid waste, instead of leaving the industrial waste within the vicinity of the plant or sending the waste to the waste landfill, which is costly, we know that the waste should be assessed for its suitability, and then the land application or recycling of waste on land is said to be the most effective and economical. She has also addressed some issues related to solid waste management and how she and her team has managed to solve that. And again, thanks to Professor Dr. Cik Fauziah for her research and contributions to the area of research as well as to the university. And we certainly believe that her research will give benefit and impact and able to address the issues associated with the management of solid waste, not only in Malaysia but also perhaps in other countries as well. And lastly, let's join me to give a round of applause to Professor Cik Fauziah on her success as well as the completion of the inaugural lecture. We wish you all the best, Prof. And inshallah, I'll meet you again in the next series of inaugural lecture. With that, thank you very much. Assalamualaikum warahmatullahi ta'ala wabarakatuh.
Thank you, Yang Berbahagia, Professor Dr. Muhammad Iqbal Saripan, Deputy Vice Chancellor, Academic and International, University Putra Malaysia. Ladies and gentlemen, that marks the end of this inaugural lecture event. On behalf of the organizing committee, I would like to extend our gratitude to Yang Berbahagia Professor Dr. Muhammad Iqbal Saripan for his willingness to chair this event today. I would also like to extend our thanks to all the audience for attending this event. And with that, I would like to invite Yang Berbahagia Professor Dr. Muhammad Iqbal Saripan and the audience to enjoy the lunch that we have prepared today. But before that, we have a special request from the staff, ex-students and students of Professor Dr. Cik Fauziah. They would like to present a memento for their appreciation towards Professor Dr. Cik Fauziah. We invite Professor Dr. Cik Fauziah on the stage. Okay, we would like to invite Puan Nurul on behalf of the faculty. Dr. Prof, another bouquet of flowers from the faculty on behalf of the staff of the Faculty of Agriculture. Before we adjourn for lunch, I would like to invite Prof Iqbal, Prof Shuko, and Prof Fauziah on the stage for a photo session. And management member as well, head of departments, deputy